So, we've got angles. Some of these definitions are going to be pretty formal, which aren't going to be entirely hugely useful for problem solving, especially the types of problems we're going to get into once we get to trig, especially. But for the sake of being a college math class, let's make a little more rigorous definitions. So a ray is a point, which we often call the vertex, and half a line. So hopefully you guys have seen a lot of this stuff in some sort of geometry class. We usually draw a point and then a ray, half a line with an arrow indicating on one side. The arrow means we assume it continues on indefinitely, so it is half a line. And then an angle is formed by two rays with a common vertex. So now we've only got one vertex, but then two rays. Yeah, the line was not very straight. And this just run into a little bit of question is what do we mean by the angle? So we actually form two angles when we form this. And so we often indicate our angles by some sort of arc that we draw between the two rays. So in this case, the smaller angle, we always call the interior angle. So I'll denote it by that Greek letter alpha there. And the exterior angle, so if we're denoting different angles, we usually draw two arcs or some sort of different notation to draw the arcs. And we can call that angle beta. So angle beta here is the exterior angle, the bigger of the two. So an angle is in standard position if one ray is on the positive x-axis. So we want to do everything relative to our Cartesian plane. And almost all angles we will be using, the vertex is at the origin. I guess we should specify that as well. So and vertex at the origin. We always have one ray along the x-axis. So we often don't draw it because it's right on the x-axis. So essentially from here on out, if we have Cartesian plane and we're drawing angles in the Cartesian plane, you always assume that one of these sides is the positive x-axis. And then what we do is we measure angles, positive angles, counterclockwise from the positive x-axis. So we call the x-axis the initial side. And then the side that we actually see, the side that ends up somewhere in the Cartesian plane, we call the terminal side. And let's just write that our positive angles measured counterclockwise from the positive x-axis. So I specifically say positive angle. So this angle alpha here, you can put a little arrow on that arc as well if we want to indicate that we are measuring from the positive x-axis. This would have a positive degree measure, something like 60 degrees, 70 degrees, looks like how I drew it. If we have negative angles, that means we are just going clockwise then. We always start at the same side, always start at the positive x-axis. So a negative angle just means we are wrapping around the plane in the opposite direction. Let me pause for 1 second. So we want to make, there's some definitions based off of the size of angles. You actually won't use most of these, but I'm sure you guys have seen these somewhere in your geometry courses. Acute angles are between 0 and 90 degrees. So this Greek letter here is a Greek letter theta, which we commonly use for angles. Right angles, we will refer to right angles as right angles. So that's a term we will use quite often. Hopefully everyone has seen that. These are 90-degree angles. Obtuse angles are bigger than 90, specifically bigger than 90, but less than 180. Usually when we reference acute and obtuse angles, we're talking about angles within a triangle. And if they're within a triangle, they don't get bigger than 180. Straight angles are 180 degrees. And then a few other key words that we will use. Coterminal angles are angles that end in the same place. And actually, I missed one here. We wanted to talk about quadrantal angles. Related to the above definitions a little bit. Quadrantal angles are angles that end, or when I say an angle ends, I mean the terminal side. And they end on one of the axes. So for example, 0 degrees is just, well, I have one side on the positive x-axis and the other side is on top of that. So it's a 0-degree angle. 90 degrees, 180 degrees, 270 degrees. That's the negative y-axis. And then it'll keep going. So you can increase or decrease by 90 degrees. So negative 90 degrees then goes down to the negative y-axis. From 270, we would be back at 360, which is again on the positive x-axis. So you'll notice that, right, these acute and obtuse, sometimes you can include 0 here. And like 90 degrees is a right angle. But most often you don't include 0 as an acute angle. 0 we would call a quadrantal angle if we draw it in the Cartesian plane. In terms of coterminal angles, they're going to differ by an integer multiple of 2 pi. Let's say, or 360 degrees. So 2 pi, we'll talk about radians here in just a second. Let's work in degrees now for at least one example. So let's say we have something like 220 degrees. If we want to find angles that are coterminal with 220 degrees. So where is 220 degrees? 220 degrees, if we were to try to draw it, we always have one side on the positive x-axis. 180 degrees is halfway around the circle, so 220 is going to be about 40 degrees beyond that. So maybe a little short of a 45-degree angle that way. And I mentioned we measure angles from the positive x-axis. Positive angles measured counterclockwise from the positive x-axis. But we can keep going around the circle. So if we were to wrap around the circle to this 220, but then continue on and go around again, we would just add 360 degrees. And we count that as a different angle. They're technically different, even though they land in the same place in the quadrant plane. So they are coterminal. The terminal side of both of these ends up in the same position. So to find the next one, we would simply add 360 to 220. And so we would get, what is that, 580? And then we can keep going. If we wanted to wrap around again, we would add 360 to that, and we would get 940. Conversely, we can go the other way. If we want to, so if I'm going here to 220, I can always unwrap and go around the circle the opposite direction and get negative angles. So if I subtract 360, the one we would get just before 220, what do we get there? So 220 minus 360, that is, what is it, negative 160? No, that's not math, 140. Okay, so let's talk about radians. Question. What is a radian? What does a radian mean? Anyone know this? It's something they often don't seem to teach in high school or emphasize.
Isn't it just another type of measurement?
It is, but how is it measured? So it's another way of measuring angles. But what does 1 radian mean?
Measurements of pi around a circle, right?
Kind of.
Leads into the unit circle, I think.
Yeah, so you get some pi's that show up halfway around a circle. 2 pi shows up if we go all the way around a circle. So let's write out the definition. So an angle measured in radians gives the ratio of the radius to the arc length. Of the subtended circle. So what do I mean by that? I mean that, so if we were to draw an angle, now we consider the angle as formed by 2 rays, so we think of these rays as extending off to infinity. But if we were to draw a circle, any circle whose center was this vertex, so we essentially go the same distance along both rays, and we draw the subtended circle here. Well, that's going to correspond to a certain radius and a certain arc length, which I'll denote by A. And I'll call the angle alpha here. So when we measure this angle in radians, really what we are doing, we are simply saying that the ratio of this arc length, if I were to walk along this arc and measure that distance, and then divide that by the radius, we would get a ratio, and that ratio is the angle measurement. We'll talk more on Wednesday about how we actually measure arc length, but it is essentially tied in to this radian concept. So in other words, what is 1 radian? 1 radian is an angle whose arc length and radius of the subtended circle, of any subtended circle, are the same. So it ends up being 1 radian is actually something like close to 60 degrees, but it's 60 and some change and something else. So essentially it means that no matter where I draw these circles, well, if I draw a bigger circle, it's going to have a bigger radius, but it's also going to have a bigger arc length. And so this, I believe, goes back all the way to the ancient Greeks that realized that the arc length and the radius grow in a constant proportion. So they're always proportional. And so an angle of 1 radian corresponds to an angle so that this distance along the arc is the same as the distance along the radius. And what the Greeks realized is that if we were to draw any circle, let me draw it this. And if we were to walk around the circle, and we were actually considering that full angle measurement, then what is the ratio of the distance we walked going around the circle relative to the radius? I actually call this one S. So we'll use S a lot for arc length as well. Then the ratio of the arc length, or of course, we could actually call this a C for circumference since we are using a full circle here, is going to be 2 pi. which also implies that halfway around the circle is going to be pi. And this gives us our conversion factor. So if we want to convert now from degrees to radians or vice versa, we're going to take advantage of the fact that 180 degrees is pi radians. One thing to note is that radians are a unitless number. I don't know if any of your high school or middle school teachers taught you this, that radians actually don't have a unit associated with them. So for pre-calc, this is one of about the only example of when we're using numbers and we're actually keeping track of units. You'll use units a lot more in your science courses, in physics, in chemistry, biology, you'll have units. Pure math courses, we often neglect units, especially in pre-calc, since we don't do too many rigorous examples. When you get to calculus, for sure, you'll do problems with rate times time and distance. And so if I'm measuring a distance, so the radius measured in feet, for example, that's a distance. Well, we're going to measure the arc length. If I were to walk along the arc, that's a distance as well. So we can measure both in feet, measure both in meters, whichever unit we typically use to measure distance. And when we compute a ratio of two distances, what happens to the units? The units go away. Oh, I can't even spell today. Unitless number. So this is the clear indicator of which unit you're using. You got to be very, very careful when we do these conversions. That's if you see the degree symbol, we're using degrees. If there is no symbol, if there's no units listed, it's automatically a ratio. It's a radian in that case. So let's see some examples, and let's talk about unit conversions a little bit more. So let's convert the following angles from one unit of measurement to the other one. So let's start off with 220 degrees. So maybe as an aside, let's do one quick unit conversion. We know that there's 12 inches in 1 foot. So I don't know how far along you guys are. This is pre-calc, so I think a lot of you guys, first semester in college here, you might probably have to take bio or chem or physics, and you'll have to do this a lot when you convert units. Your units behave many ways like variables, that they will cancel when they divide, and in many ways that's what you're looking for when you convert from one unit to another. So for example, let's say I have a person who is 6 feet tall. How do we want to convert that if we want to find the number of inches? A lot of times what people will do is draw these boxes. This is a helpful way to organize things. You don't have to if you're used to doing unit conversions, but I do want to show you guys this, as I found it helps a lot of students just to keep their work organized. Whatever unit you want to convert, start off with in the top left. Then you put your conversions in these other boxes. So we're just converting one unit, so we're only going to have to add another box. Sometimes you're converting speeds though, like miles per hour to kilometers per second or meters per second, in which case we will have to convert both the kilometers to feet or something like that, and then as well as the time from hours to seconds or something like that. So sometimes it helps to keep extra boxes. And if you want, let me know. I can help you convert or do another example like that if you want after class or during office hours. But let's just convert feet to inches. So what do you want to do? I want to get rid of the feet. So from your unit conversion, put that in the denominator because I want those two to cancel. I want to be left with inches, so we put that on top. It's essentially the same as finding a common denominator for fractions, but in a weird way, because these numbers, the numbers are different, but because we're using different units of measurement, these two numbers are the same quantity. And since they're the same quantity, a number or quantity divided by itself is just one. We're not changing the actual amount expressed in this notation. We're just changing the units. And so what do you get when you simplify it? You can essentially multiply straight across. And if you think of it like 6 feet, 12 inches over 1 foot, and if you think of the units like variables, the feet will cancel and we are left with 6 times 12 inches. So we're left with 72 inches. Do the same thing for our degrees and radians now. So if we want to convert 220 degrees, I'll put 220 in the left. I want to get rid of the degrees. So I'll put my unit conversion is pi equals 180, right? Pi radians equals 180. So you want to make a fraction out of that. And the way the fraction goes is essentially dictated by whatever you're starting with and what do you want to convert. Since I want to get rid of the degrees, I put the 180 degrees in the denominator, put the other one in the numerator, or pi. And then now we multiply straight across. We'll get 220 pi over 180. The degrees then cancel out. And now we just got to simplify the fraction. So it looks like we got 22 over 18. So 11 over 9 pi. Or if you like to put the pi's in the numerator, 11 pi over 9. Either of those is fine. Likewise, we can go back the other way. If we give you an angle, or if we say a number represents an angle, if there's no units attached to it, it's radians. So this pi over 8 is a radian measure. And if we want to convert it to degrees, we want to put our radians then in the denominator. Now, radians are unitless, so we don't write a unit there. So they don't cancel. There's nothing to divide out. But we do want to be left with a degrees. And so we make sure we put the degrees in the numerator so those units will stick around. And so if we were to multiply this out, it would be pi over 8 times 180 degrees divided by pi. So we're just multiplying straight across. I essentially just kind of put that 8 in the denominator so as not to deal with too fancy of fractions. Pi's will cancel. We're left with 180 over 8, which looks like it is going to be 90 over 4, or 45 over 2 degrees. Okay, so let's see 2 more of these. And these are the ones we want to be careful of because I'm going to write pi degrees. Our common mistake is that if we see pi, we immediately think it's radians. These pi's, remember, appear because of this magical computation that the ancient Greeks figured out, that the ratio of the arc length of a circle, or the circumference of a circle, to the radius is 2 pi. And so oftentimes when we are measuring angles in radians, we are getting fractions of a circle, so we're getting fractions of 2 pi. And so these pi's will come up very often when we measure radians. But it doesn't signify radians. So I can still use radian measurements without having pi's in there, and vice versa. So we can have degree measurements that have pi. Pi is just a number, right? It's 3.14159 with some infinitely many long decimals. So pi degrees, we have a degree measure. So it's something like 3.14 degrees. If we want to convert it, we need to get rid of the degrees. So the 180 degrees goes in the denominator. So those degrees will cancel, and we'll get another pi in the numerator. And so when we multiply things out, the degrees will cancel. I've got pi squared now in the numerator and 180 in the denominator. So that's how many radians it is, pi squared over 180. So likewise, if you don't see pi's, it doesn't necessarily mean that we're in degrees. If I give you a number 4, and I say this is an angle measurement, what's that mean? It means radians, because there's no degrees attached. I didn't say 4 degrees, I just said 4. That implies radians. So if it's 4 radians and we want to convert it to degrees, we need degrees, so we'll put that in our numerator, our 180 degrees. Put the other side of the conversion factor, pi radians, in the denominator, and then multiply everything straight across. So 4 times 180, that gives 720 over pi degrees. And we can compute that out if we want to get a decimal approximation for this. So it looks like it's going to be about 229.18 degrees. Right, just the number is what pi is. Any questions on any of that? I guess one thing we do want to mention as well, I think most people understand this, but we want to define our coordinates, or excuse me, our quadrants when we measure angle. We'll be using these quite a bit once we get into our trig functions. So it just goes counterclockwise, 1, 2, 3, and 4. Quadrants 1, between 0 and 90 degrees. '90 to 180. Quadrant 2, 180 to 270. Quadrant 3. And then quadrant 4, 270 to 360. Now notice I don't have any equal signs there. So where's a 0 degree angle? So remember, if it lands on the axis, so if it's 0 degrees, 90 degrees, 180, 270, or any coterminal angle with those, we just call those quadrantal angles. So if it lands on an axis, doesn't land in one of the quadrants, so we'll just call it quadrantal angles. And you can specify if you want to be specific on any of your problems. You could say it's a quadrantal angle ending on the positive x-axis, or you could say a quadrantal angle with the negative y-axis. So whichever one it lands on. Any questions? Let's write down, I guess, real quick. Same thing. Let's use radians. So pi over 2 radians is 90 degrees. Pi is 180. Just pi. 3 pi over 2 is 270. and 2 pi 180. So if you're not comfortable, I would say definitely practice using using radians and using fractions of radians. We'll talk about some useful tips on how to count in fractions of radians once we get a little more into trig and reference angles next week. I found it pretty effective to be able to teach common counting methods and how to count in fractions of pi, which will help out with a lot of the computations. Any questions on any of that?